Efficiency of time. Time's always our limiting reagent. Always. Okay. Oh. That's right. Have holiday stuff on your desk because I didn't get to check it a couple days ago. Too big cold. I'm going to review 6 through 8 and ask you some questions about things that you had issues with on those FRQs. After that, we're going to prepare our lab, which is really an easy lab today. You're making an electrolytic cell, and you're going to have one solution that's assigned to your group. And then from there, we're going to look at other people's cells that they set up together on a different line. Okay? Ready? All right, so in terms of drawing, we didn't get to like straight up draw our own yesterday. So in reference to drawing an electrolytic cell, who kind of had a single well setup? Okay, so no double, like it's not two different chambers, just one chamber. And then you have to use inner electrodes, which platinum is generally the choice for that. So I just labeled showed two different electrodes, anode and cathode, just not these, not copper, not the solutions, ions even. Most of the time we can use an inert unless somehow it says like you have a silver cathode or a copper cathode. Regardless, we have a little separation, which we called yesterday a what? Porous barrier, which we know that means ions can flow back and forth because that's how they transport to be deposited on one side or the other. I drew mine just a little opposite than normal because I wanted you guys to be comfortable looking at cathode on the left and on the right. And since we have a external source of energy, I kind of drawn a battery up here. This is like how you draw batteries in physics and true battery drawings. Or circuit drawings. So I just put my voltage source up here, which is the galvanic cell. So the anode sends electrons towards the cathode of the galvanic, and then the anode of the galvanic sends electrons to the cathode of the electrolytic. So what's the half reaction happening at the anode with copper 2 chloride? Cl minus, okay, yields chlorine gas and 2 electrons. So then I'm going to get 2 right there, correct? So I've actually drawn bubbles to indicate that evidence or an observation that you would see. So I'm expecting in your lab you're drawing some little evidences or observations that would be very clearly seen in the lab, and then you can depict them in the picture. And then at the cathode, what's happening? What's the half reaction? Copper 2 plus 2 electrons yields copper solid, right? And I show that here by the little fibers or the plating out of the copper. We yesterday did not get a chance to do this. Do you guys have your reduction potential list readily available? So we're going to calculate E cell, E naught cell the same exact way we did with galvanic. Who's oxidized here? Chlorine. And who's reduced? Copper. So how do we find E cell? E what? E of the reduced half reaction minus E of the oxidized half reaction. So what is the volts or the E of copper? 0.34? We use that one a lot. 0.3 what? Okay. And what is it for chlorine? 1.359. Okay, so what am I plugging in for E red, or the cathode? Okay, so 0.337 volts. I'm going to subtract the anode, so that's 1.359. And can somebody calculate that real fast? What is it? 1.022. Okay, so how do we know that this is electrolytic just by looking at the E cell value? It's negative, right? So that's one thing I just wanted to emphasize, that you will still be expected to calculate E cell in electrolytic cells, but we know that the galvanic cell is providing energy because this is not going to happen by itself. It's not spontaneous. It's not thermodynamically favorable. So that's why we have the galvanic cell to assist it. Are we okay with this? All right, you'll be doing like 7 of these today. So if you're not, you should hopefully be good at the end. Okay, so the next one had like 3 questions. So you had an aqueous and chloride solution. You're making chlorine gas, so we knew that chlorine gas was being produced from chloride. And then it asked to find moles of sodium hydroxide produced, which is kind of weird because it's a sodium ion. So you had to think about how sodium hydroxide could even be attempted to be formed, which is actually from the assistance of water being oxidized or reduced. And then the pH, which means thinking about H plus or OH minus, one or the other. So at first you're thinking, okay, sodium chloride, you know that this is not truly what's happening because this is not molten, this is aqueous, so we know potentially water is a player in the game. But if you just write out the chloride going to chlorine gas, even without this, so like this is not going to happen because sodium ion is not going to form sodium solid, because what will it do in aqueous solution? Explode, right? Make fire. But the chloride itself makes chlorine gas, your 2 electrons, and as the way they calculate your liters of chlorine gas at STP. At STP, what number comes to mind when you're looking at gases? 20.4. So you got your minutes to seconds using the amperes, and then I always use the estimated value. So if your R values are slightly off, it's totally fine. It's just because I usually don't use the full value. Why? Somebody told me to do it one time, and I continue. And then your chlorine has a 1:2 ratio with itself, chlorine gas, and it's 2 moles of electrons that are exchanged. And then you use 22.4 liters, and you get approximately 8.1 liters. Are we okay on that process? Okay. So at first I wrote the sodium because you generally think of those half reactions being anode and cathode. But since this is happening in aqueous solution, water is actually the player at the cathode, because sodium can't be. Sodium ion's not going to make sodium solid because it's going to be explosive. So if it does not say it's in acidic solution, so we're taking water and we're undergoing the the reduction of water. So it's gaining 2 electrons, making hydrogen gas and hydroxide ion. This was what we wrote in the table. Remember that table? This is like the last one. So we're going to take this and we're going to let it make hydroxide. That's the only way we're going to make hydroxide to make sodium hydroxide, which was the question. Sodium hydroxide. So actually what's happening is the sodium that was kind of just chilling from the sodium chloride solution is able to bond with the hydroxide ion that's produced. So basically you have a half reaction. You have the electrons that are related to the 2 hydroxides that are formed. You're just doing your stoic again, but with reference to that mole ratio. So it's still said like 75 minutes, 75 or 750? 75, I think that's a decimal. And you're still going through your stoics over minutes to seconds to coulombs to moles of electrons, but this is the new ratio. It's 2 moles of hydroxide are related to 2 moles of electrons. So from that, and then with the presence of sodium ion just hanging in solution, you're able to make sodium hydroxide. So that's moles, 0.723 moles. We go okay? All right. So finally, we're going to put the battery together. We have the anode, which is the chlorine, and you have your cathode, which is the water. And so this is truly what's happening. I just wanted to write out my entire thought process. I'm like, how would I just immediately get here? You don't immediately get here to think about it. And once you have the total reaction, you have everything together. But at this point, it's asking for pH. We don't have any H plus present. We have OH minus present though. So because we have this many moles of hydroxide, and this occurred in a 500 milliliter solution, so 0.5 liters, you take your moles of hydroxide divided by your liters of solution, and you get hydroxide 1.446 molar, and then from there find pH. So since you have OH, you're going to find it's 14 minus POH equals pH. So that's negative log of the OH to give you POH. Do you remember a little bit of pH? It's coming back. So that's a really strongly basic solution, because it's actually a super base that's slightly higher than 14. Lastly, and this is what I want to talk about because there's one part on the bottom that I need to adjust for you guys on the key. You have your molten lithium chloride. So you only have 2 options here. These are the easier ones. You have your cathode, which is going to have the cation, the anode, which is going to use the anion. And so I just kind of wrote up the 2 half reactions so we know what's going on. And then for the total reaction, lithium plus 2 chloride, yields lithium solid chlorine gas. Okay, so we have our full reaction because we have our two half reactions written. We are given 24 hours and 7.5 times 10 to the 4th amps. So utilizing the ratio to get to lithium itself, we're just looking at the lithium half reaction. So we move along through stoic, we get to this place here with 1 mole of lithium and 1 mole of electrons. Then getting to grams, go from moles to grams using the 6.94 grams, but 7 grams of lithium. But since it was only running 85% efficient, then we basically multiplying by 0.85 at the end. So multiplying by 0.85 is the same as 85 over 100. So you should get approximately 4 times 10 to the 9th grams of lithium produced. So that's how they extract or produce pure metals from molten solutions. Molten, I won't say solutions, but molten substances. So once we have that piece, I think most of you guys just did your stoic and probably achieved that just fine. The last piece, though, asks for energy. I think that's how it's phrased. Energy of the system. So if we have delta G is equal to negative NFE, we know that delta G and work are related through their kind of inverse relationship, but you're producing energy to be used to do work. So I just kind of put work in here to show that work. You could also ask for work separately from energy. So essentially work, because it's negatively related to delta G, work is equal to NFE. So in here, on my key, I didn't multiply by 2. I think I only had 1. So I fixed it here. But the system with lithium and chloride had 2 electrons total transfer. So that's the 2. So N has to be total moles transferred. And then multiply by your Faraday constant. And then it told you E cell. You didn't have to calculate it yourself. I'm pretty sure it told you that in the problem. So once you plug that in, you should get 1.45 times 10 to the 6 coulomb volts, because moles electrons cancel, but remember, define it as energy, so define it as joules. So that's 1.45 times 10 to the 6 joules. All right, major, like, I'm not sure what to do questions. Yeah. So we only barely practiced yesterday. Today, hopefully that will clarify, because you're looking at aqueous solutions or molten substances. So you have to look at the chart until you're comfortable with knowing in your head. When I give you copper 2 sulfate solution, you should be able to think, okay, here's my priority for anode, here's my priority for cathode. That's just going to take us some more practice, but today's lab, hopefully we'll handle that. All right, are you okay right now? All right, so lab stuff. I have lab notes to hand back to you. I want to discuss those last 2 labs, but if I get to it in the class today, I will. If not, I can do it tomorrow, the next day. So let's talk real fast what I'm asking of you. So you guys are going to have these 6 solutions, or these 6 solutions, and of the 6, you're going to start with 1, and you're going to first predict what's going to happen with that solution using your priority list. You're going to draw the cell, the electrolytic cell. You're going to predict what you would observe, and then from that observation, you're then going to do it. Like, you're going to set up the cell, you're going to put a battery connection to it, make a circuit, and you're going to watch for those observations. So I'll assign you one of these in a second, but write down what I'm expecting of you, okay? So I'm going to give you a group in just a second. You're going to predict the half reactions. Make yourself a list here. You guys can read. So once you get your half reactions, you're going to draw your cell, just like that number 6 on homework last night, single well with multiple observations made. And then instead of putting it right in your lab notebook first, I want you guys just to take a piece of paper, just a white piece of paper, like computer paper, and draw your cell big enough so it's, all your observations can be clearly noted. And you're going to fold it in half, and you're going to leave it in front of your lab setup. So as we do a rotation, because not everybody's going to set up the same cell 6 times, we can look at the cell, we can make our mental predictions, and we can look at your answer key. We can see that clearly. So that's why I want you to put it on a piece of white paper so you can leave that at the station. So with that, you're going to have those half reactions. You'll have your total reaction. You'll have your E cell value, not. And you need to test it to verify that's right. So once you predicted it and say, let's say you're wrong, you need to fix that in your white paper before we proceed. It's pretty easy. Other groups are going to look at your work though, so make sure it's clear. Okie dokie? All right, so I can come back here in a second. With your cell setup, are you good on how to set this up now, like drawing wise? I just wanted to give you another example of how that looks. You can indicate the electrolytes present, you can indicate the cathode and indicate the observations made. I can go back here as well. So I'm just going to count off so we can make this happen. So we have 6, so I'm going to give you number 1 through 6. Ready? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, get with your ones. Go. You guys have 6 last stations. Go ahead and get your drawing information first, and I'll hand out materials. Oh, grab your lab notebook on the way. They're on the other side. You can see what your assignment is on the board. So white paper is going to be right, actually I'll bring it to you. Hold your fingers up on your hands so you know where you are. There's 6 lab stations, so if you know what station you're here, then you'll be back. Right now, they're all solutions. All of our solutions. You should be close to done, and but someone should start drawing if you want markers and such. You know where they are. will eventually reach equilibrium.
Oh, yeah, yeah. That's all. We are number one.
Alright, so listen up for the last thing, and you can go ahead and get started in just a hot second, okay? So I've placed the building of the electrolytic cell controls at your station. But the way it will work is that you have a little cell well. Make sure it's like your desk here. So that'll be when you pour your solution in. Don't fill it to the brim, right? About halfway is good. So your solutions have been provided for you. And then you have your alligator clips, which will be hooked up to the 9-volt battery. You look at the positive and negative of the 9-volt battery. Usually help you determine who's anode and cathode. You have to think about it first. Your alligator clips, just kind of, you open them and you can either brace them on the entire terminal, or you can put it on like, just grasp one side of the terminal. So like, it'll clamp there. So don't put the alligator clip on both sides, put it one on each side. So the alligator clips will not be the conducting agent though for your solution. I'm giving you a little bit of graphite, so pencil lead. So just take one, you don't need really long ones. You just take one piece of pencil lead and break it in half, and you'll clamp those two halves into your alligator clips, and then you'll use your alligator clips, and you'll tuck your pencil lead right into your solution and look for observation. Now, if you can tell that observation, you're good to go. Something might be produced at your anode or cathode that would be not observable to the naked eye. So I also have provided methyl orange, phenolphthalein, and have matches too. If there's something that's produced that you could potentially test with a match. The only thing is I'm not sure if you're making enough to actually detect it, but hey, it's fine, right? So once you're good to go, goggles on, set it up, and then look at your observations and see if you matches your picture. If you get started and there's nothing happening, I would one, try the opposite terminal, because I'm guessing it's set up incorrect. Or two, your battery's dead and I have more batteries. I'm not checking the life of the battery's dead.
So what did you say? We're not.
Yeah. You should be testing your solutions now, folks. Let's
Yellow or red?
Alright, if you have finished yours and you want to leave your battery set up and not in solution, you can go talk to another group and see what happened in there. Like right now. You need to draw yourself. Alright, I'll make a deal with you. Listen up. You need to draw 3 cells out of the 6. Go. 3 out of 6. Flutter around. Go see what else others are doing. Like I said, if you don't
gas bubble and one of those It's not a problem.
Third cell done in a couple minutes. Third cell done in a couple minutes.
Means we're getting water on here. So 2H, H2 gas. That's our